Hello, thank you for attending this webinar by Mahr, the leader in precision surface measurement. Today's webinar is Surface Measurement Speaks the Language of Productivity, Applying Surface Measurement at the Point of Manufacture. I'm George Schuetz, Precision Gauge Director at Mahr in Providence, Rhode Island. And anytime that you might have a question or a comment, feel free to use the chat feature and I will respond to your question after the webinar by email. So let's begin. Today's agenda is learning about surface finish and why we measure it. We're going to talk about the types of surface tools. We'll see some advances in making surface tools easier for people to use. We're going to learn how tools can provide data integrity, how two-way communication is used to automate the measurement process, and we're going to see some ways to implement surface tools into automated process and integrate them into Industry 4.0. So let's begin. It's very important to monitor surface finish today because as we can see, products for aerospace, electronics, automotive, medical, precision manufacturing require tighter and tighter tolerances. And this chart shows us that since the 40s, tolerances have become a fraction of what they used to be. So as these dimensional tolerances tighten, form and surface errors become more significant. And thus it becomes more important to measure things like form and surface. So every surface has some function, and unless it is measured, one will not know if the product will perform as it is desired. Now, why do we control surface? Well, there's a number of different reasons. Appearance is a common one because surface finish affects reflectivity or consistency. So this picture on the right here shows a shiny part and a rather dull part. And those are all characteristics of what surface finish can do to a surface. So people want to control the consistency of how the part looks, so they will monitor the surface finish. Another important function is surface adherence of coatings. Now, if the surface is too smooth, the paint might not stick. If the surface is too rough, the paint might not cover those surfaces. So we have to monitor that surface to make sure that the paint covers the surface properly. There's also surface interaction. You know, as sliding surfaces move together, you want to have a surface that's smooth so that you can have less frictions of that surface. But you might want to create special surfaces that do have a lot of mating surface, a lot of bearing area, but there might be some grooves or small surface valleys put into that surface so that oil can be there and help lubricate the movement of the two surfaces. So surface interaction is a very important way or reason to monitor surface finish. And it helps us to maximize processes. You know, it helps us to fine-tune the speeds and feeds of the machine so that we can get the best production from the cutting tools while still maintaining the surface quality. And if we do find surface problems, that can help us diagnose process problems because there might be something from the machine tool causing the surface finish errors. So lots of reasons to control surface finish. Now, where does surface finish come from? Well, like I said, it comes from the manufacturing processes. And a lathe is a very typical manufacturing process, which consists of a bed or a way that the head is moving, the carriage is moving on. There's some motors, there's a gearbox, belts and pulleys and bearings and rotating spindle. There's a cutting tool, so that there's lots of components to that manufacturing process. And each one of them puts a little bit of surface finish into the part being manufactured. So the roughness could be the cutting tool marks. We could have some vibration from the bearings or the gearbox, and straightness of the ways can also be put onto the part that we're measuring. So each one of those components gets added together, and you can see that they all relate to the total part profile for surface finish. Now, in the past, surface finish used to be measured by a scratch test or scratch standards. People would use their thumb on these standards and compare the part to the standard to get an idea how good that part was. Well, today there are some very sophisticated methods for making surface finish measurements. There's mechanical contact tools to do that, and there's also some new optical non-contact tools to do that. But today we're going to focus primarily on the mechanical contact methods. So there are two contact methods for surface roughness evaluation. There's a skidded way of measuring surface, and there's a skidless measurement way. The skidded is the most common, and in that type, a probe, which consists of a very precise stylus, is pulled over a part. That stylus passes through a skid which follows the profile of the part. So because it follows the profile of the part, all we're going to measure is the actual surface roughness. So skidded instruments measure only roughness parameters. Waviness is filtered out of the skid because it follows the surface. And like I said, most portable instruments use this skidded method. Now, a skidless measurement has a very precise, straight reference datum as part of the drive system. And the stylus and probe is just moved over the part. And now we're comparing the surface roughness to that precise datum. So now we can measure roughness, waviness, and profile from that tool. So you can get a lot more information from this type of skidless measurement system. But like I said, the majority of surface measurement is done with skidded instruments. It provides a simple number-based result which fulfills the needs for most part qualification. But for critical application, process development, or quality issues, sometimes the skidless systems offer far more information. Now, when we look at surfaces, there's a number of different parameters. In fact, there's nearly 100 parameters for surface finish evaluation. There are surfaces parameters for stability of the manufacturing process, functional characteristics of the surface, analytical capabilities of the instruments. But by far the most common parameter used for surface roughness in the United States anyways is R sub A, or roughness average. Since the roughness profile contains those peaks and valleys caused by the cutting tool of different heights, the averaging method is used to quantify the surface. This gives us a good general indication of the surface. It's easiest to understand and visualize. It's easy qualified with a single number, and it's read very simply, and just like 65 degrees. In this case, the RA is equal to 75 microinches. So the number and the parameter tell us what that surface finish is. Very easy to understand. But there are always issues, with RA, since it uses an averaging system, you can have very different looking surfaces that do have the same RA number. So surface performance could be different due to this bearing contact effect. You can see these peaks and valleys have the same heights, but on the picture on the right, this has a larger bearing area, and that would perform much better in a turning or a moving parts between themselves better than the picture on the left. So RA is often specified and is valuable for monitoring process stability, but there may be other parameters needed to monitor the surface function. Now, what's happened in the past 20, 25 years or so? We're starting to move surface finish measurement to the point of manufacture. Historically, surface finish measurement was delegated to complex and expensive instruments in the quality lab. And these instruments required trained and skilled operators. Often the parts had to be sent to the lab for inspection, so there was a long lag time between the part being manufactured and being inspected. And often bad processes would continue while those parts are being measured. So there's a potential for scrap and continued production and the parts being measured. So this is really a go, no-go process, because by the time the parts are measured, they're either good or they're bad, and potentially more bad parts are being manufactured. But today, surface finish tools are moving out to the point of manufacture. The new tools today are portable. They have very similar or just the same capabilities of some lab instruments. They're really designed for ease of use, and they can be dedicated to specific shop floor measuring tasks. However, machinists are, they're not necessarily trained quality control inspectors. They're trained as being machinists. So what we have to do today is make sure that today's surface finish tools have to be simple and easy to use in terms of their operation and their orientation for easy and proper measurement. And surface finish is also becoming part of Industry 4.0 because we're all trying to have the same goals. We want networked factory with intelligent machines, measuring tools, gauging instruments, and all being interlinked by IT to share information. They want production improvements through simple and complex automation, making everything faster and more flexible. We want process reliability where we can monitor and prevent downtime in terms of machines, but also preventing bad parts. And we want machining efficiency, reducing steps, speeding movements, making easy measurements for the operator. And we're starting to get that. Today's tools, especially those produced by Mahr, whether their wireless integration or ease of use capabilities, are all part of a networked factory and Industry 4.0. Now, how can we guarantee success with surface finish tools at the point of manufacture? What we do is we try and make intelligent measuring tools, and we employ a user-established interface so that it's kind of like a smartphone. People today are very comfortable using smartphones. So users with little prior knowledge of quality control will find systems easy to use, just like they're doing today with the tools that they have. And we can also provide lockout features to prevent operators from setting wrong parameters or not using the instruments properly. So today's machinists live in that digital world. They're all familiar with smartphones. We try and make the tools act like smartphones. So by using swipes and buttons and different screen formats, rotating the screen, for example, it's very easy to set up and use these instruments. And the measuring instruments all have the same parameters and are just as powerful as some of the lab equipment that we manufacture. So you can see there's some screens down here. They look very much like a smartphone, different orientations, different graphs, a very clear, easy to use user interface. And not only can we make the measurements, but we can easily qualify or quantify the results for the user. So there can be tolerance limits for the selected parameters. We can display results, make a printout, or transfer that information for data collection. And we can easily create surface analysis graphs, bearing area curves, for example, and they can all be visualized very quickly by the user, plus get the single-digit quantitative results. So with over 100 roughness parameter available, certain processes or parts may require different specific part parameters. Now, even with the most easy of use instrument, this can be a complex setup function. So what we try and do is take away that time-consuming process to the machinist and design that with using different tools and making that setup parameter easy. One way of doing that is employing a QR or barcode scanner where we can automate parameter setup. So, typically a lot of parts will go through the shop, and we can have with it a workflow sheet. And on that workflow sheet, you can have a barcode. The operator would get that set of parts to be manufactured and measured. He would scan the work process. The instrument would load all the parameters needed for that measurement, and there's no operator influence or setup required to set that unit up to make those measurements. So scanning with the barcode will read the information and set the profiling information. There's some other things that are happening in industry. There are some new standards out there, this International Automotive Task Force, for example, and their goal is to try and tie all the loose end pieces of the inspection or manufacturing process together. So some of the important features of these new standards are verification that the process are being carried out as intended, verification that monitoring and measurement equipment is fit for the purpose, and monitoring of the measurement activities and results. So it's very, typically people will measure a part, they'll have a piece of equipment to measure it, they'll record the data, maybe get the time that measurement was made, and that file is complete. But there is a missing element to that. There's no traceability that the right instrument that's under calibration control made that measurement. So what we can do now is start thinking about traceability of the products that are assigned to the measuring equipment for those production batches. And we can build that information into the surface finish equipment. So now we can not only transfer the measurement results to the data collection tools, but we can also transfer the unique serial number and identifier of the measuring equipment. So now, as part of that data collection package, we can know who made the measurement, when it was made, what the results are, and that it was made by the right tool to do that instrument. So now the quality systems have the measurement results, they have the serial and part number of the equipment, date and time of the measurement. That whole measuring process is tied together and provided, ensuring a good quality control of the data. Now, another important thing is ability to start thinking about building or controlling and making the measurement equipment, the surface measuring equipment, an active part of the measuring process. So we can do in an automated factory, we can have the gauges be intelligent enough that they can take data and be sent controls and functions remotely. So we can build interfaces into the surface finish measuring tools to help do that. So some of those controls could be remote control to start the measurement, changing the setup parameters for different parts, requesting settings and data to verify the setup, and also act as a text field for sending information to the operator. For example, that a measurement might be transferred, but they could get a message back saying that that's not a good measurement. Maybe you should take it again. And all these controlling functions are simply ASCII control commands, and the whole measuring process can be taken over and controlled by SPC programs, by a PLC as part of an automated process, or by gaging software platforms as part of automatic gauges. So the surface finish equipment becomes part of a total automated measuring system. Now, how else can we help automate the process? Well, a surface system used by a trained technician may not perform well in the hands of a machinist. There's sometimes alignment features that you have to worry about. And general purpose mobile surface measuring instruments may not be the best choice because they're hard to align. They can be a timely process to get the alignment. And all those steps takes away from the machinist manufacturing parts, but that's his primarily goal. So this is where manufacturing facilities are looking to reduce the amount of interactions within the part. And we can start helping that by making dedicated surface finish tools. Now, normally when you think of automation and custom gauges, one envisions these large gauging stations with moving parts into position, aligning and positioning the part, measuring the part parameter, classifying and sorting the parts. But in reality, automation means a lot of different things. It could mean that, but simply making it easier for the operator to use and make his measurements is really helping to automate the process. So we can do things to create special gaging apparatus or alignment fixtures. We can do things with process handling, all in the effort to make the gauging dedicated, foolproof, fast, and easy for the operator to use. Now, one of the goals might be replacing or shorten operator involvement. So a simple custom fixture to help align and position the part, protect the probe, manually or remotely control the start of the measuring cycle, and collect and record that measurement data are all ways to bring the automation to that measurement. Here's an example of a little fixture gauge which has a probe. The part is put onto the fixture. It has the surface tool part of it. It has probe protection. There's no alignment, and making the measurement very foolproof for the operator, automating the measuring process. Another way of doing that is to create templates for special gauging applications. And a template that might fit on the top of this engine component, for example, it would help align and position the gauge in each of the various locations at the correct position. There's only one way to mount the gauge and mount the template, and it helps to protect the probe. So this ensures setting the gauge at the right spots in a very easy manner, aligning it properly, protecting the probe, and there's tremendous savings realized in each part measurement. You can imagine in a crankshaft bore, for example, that it would be very difficult to align a surface finish probe a couple of feet potentially into the bore. But we can create special plug gauges with the surface probe built into it, and this helps align and position the probe by the plug. There are depth stops to position it properly at each depth, and in all measurements the probe is retracted and protected while it is positioned to the next land that it has to measure. So again, saving is realized by the simple placement and ease of use to the operator. We can also create some semi-automatic surface finish gauges, and ones that are kind of the in-between systems, where they combine the automation of the PLC to collect the data, but they also have some manual influence for positioning the tooling. So these in-between systems, they have the capabilities for external serial commands from a PLC to begin the measuring process and parameter calculation. It operates in a guided sequence where the operator is shown pictorially where to place the gauging equipment. So therefore, it's kind of under control by both the user and the PLC for the start and the measuring control. So through pictures, interface, user interface, the operator can be guided through the measuring process, but the PLC is collecting all the measurement data for him. So again, pictorially, we can use the PLC is there. It's waiting for the data to transfer and storage. It's all networked, and it's act as an intelligent source of the data. It can store the data at the gauge itself until the network is ready to collect the information for that part. And it can also act as a message board for the user to lead them through the gauging operation. So a semi-automated gauging system. But then we can go to fully automated surface gauges, where we really take all the capabilities of surface finish tools and build them into an automated measuring process. Now there's two levels of automated customization for surface finish. There's the automation designed as a standalone measuring station, or the surface gauge can be a component in a dimensional gauge where the part is presented to the surface gauge for measurement, and this whole operation is controlled by a PLC running the whole gauging station. So for these standalone systems, these are truly designed for Industry 4.0 in mind. They have communication capabilities in place. They have capabilities for external serial commands from a PLC to begin the measuring process and parameter calculations. They wait for when the PLC is available to begin its data transfer and storage. They're all networked and act as an intelligent source of data. They're always online, and they know when parts are coming, the part serial numbers, and the ability to tie all the data together. They usually do not include the part movement to the gauge. They're often robot or pallet loaded automatically. They have all the surface gauging components in one place. They can have the ability to be programmed for multiple parts using different fixturing. They have the ability to automatically select alternative probe systems for the right surface being measured. And they stand alone in that they control their internal movements to bring the probe to the part. Within these gauges, there are slides and rotary tables to help position the part to the probe. They're specifically tailored for speeding the measurement process, and they're designed for part tolerance and the environmental conditions. So they can have enclosures, vibration pads, and so forth to ensure that they work well at the point of manufacture. And we can also offer fully automated surface gauging stations, really for the industry of the future, for the lights out operation. These are fully automatic gauges that are ideal solution for these types of parts. You know, places where operators would spend a lot of time positioning the part to a probe. Large or small parts would be difficult to manipulate. Or if we have lots of parts and pallets, it's great for measuring these in sequence very quickly. So interchangeable Probing allows for various features to be measured. This can be a lights out operation measuring multiple pallets over time with absolutely no operator involvement. Now, some ideas where these examples would be used would be parts with deep or hidden bores or surfaces like fuel injection bodies. Deep probes can measure contour and roughness of the entire cone and nozzle. Just think of how difficult it would be for an operator to try and align this type of part to the probe. Especially when the probes go down to a 0.6 millimeter diameter, it'd be virtually impossible to manually do that type of measurement very quickly in a production environment. And also you can think of small medical parts. These could be high volume, very small parts with small holes, very difficult to align, but an automated system could do that very quickly and easily. So the benefits of an automated surface measuring station: reliability, flexibility, and speed. Measurements tasks are with very tight tolerances or small or large parts can be done very quickly. Fast measurements without any complex setup because the setups are programmed in there and pulled up by part number. There's automatic alignment and positioning of the work pieces. And because they're all automated and driven, there's no risk of having probe or drive or arm damage. So you got all the capabilities of in-process measurement. You can do statistical evaluation of each feature with complete feedback to the machining tools to potentially change the process to improve the results. Because these gauges are all under control, they have a serial number. This all can be collected as part of the measurement results, meeting the current standards. And complex and diverse measuring results can be obtained with no operator influence. So today we've learned a lot of different things. We've learned the importance of surface finish and why we measure it. How today's surface finish gauges have the communication tools to be part of Industry 4.0. How dedicated surface gauging speeds the measuring process, whether it be a simple automation or a fully automated measuring system. We've learned how surface gauges can be built into automated stations, are an integral part of Industry 4.0. And now surface finish is really truly a point of manufacture inspection tool so that we can quickly measure and qualify the parts at the point of manufacture. So I'd like to thank you for your attention and listening to this webinar by Mahr, and we hope to see you again in the future.